Hello again, folks, in 114. Today we're going to be starting Chapter 12. This will be the last 2 weeks of the Summer Session 1 course. Alright, so we're doing 12.1. Here is the calendar, just to validate that point. Today is Monday, June 21st, which I want to say is, if not the first day of summer, then Sunday was. So we'll be covering section 12.1. And the packet should look like this. This is an overview I'm going to refer to probably several times through the next 2 weeks, but this will give you an idea of where we're headed, and I'll go through that. The actual material starts on this page. I might annotate this. This is purposely blank down here because I want to illustrate some points. So you can kind of think of this as a worksheet, it's just not very complicated. Alright, but I'll go through this. There's some room for definitions. I reserved that for certain words. This is an example I stole from some of the book that illustrates population versus sample. Right. And then there's the actual meat of this, which is the different sampling methods that we'll discuss, okay, with some examples. Then there's a couple of brief word problems, the parts of one, and some suggestions for detecting misuse of statistics. Okay, so we'll go through that. All right, turn this on and adjust the light size on those. So the camera is approximately in the right place. Oh, I didn't connect it, of course. Okay. Geez, I'm gonna get rid of. Sorry, bear with me. Oh, there we go. Okay. I'll do that some other time. Okay. Let me refer back to this timeline that I've been working on. This is, again, it's not something that you're responsible for, but it's just to give you some inkling as to what we're doing, where we've been, where we're going, where we are now. Okay. I'm contending with the natural daylight, so I'm going to try to block it out a little bit better. There you go, that's a wee bit stronger, I think. Alright. Now, earlier in the course, we had been covering Babylonian arithmetic, Mayan numerals and such. At least Babylonian, which is derived from Sumerian, would be in this time frame, and we might regard that as ancient math, which is basically arithmetic. More recently, we got into geometry, which is also technically ancient. And then there's a different type of geometry, which is sort of basically, you might say, Greek geometry, which is based upon logic, less practical. A while back, we had covered what you might regard as medieval math, which is algebra. Alright, we'll always refer back to that, of course. And where we are now is basically here. Alright, the type of math that primarily originates from about 1600 forward. So this is where chapter 12 is. Alright, and we're covering statistics. Now, the truth of the matter is, you know, math is math, and it's been around for eternity. So some semblance of statistics has existed prior to this, but That's about the time when maybe the actual name originated, right? What you might regard as a sort of proto-statistics. Originated also in the ancient, right? The Egyptians and the Romans, for example, and the Babylonians as well, took censuses. So to take a census is to collect data, really, just maybe not calling it that. All right. So think of that as being sort of an ancient proto-statistics, if you will. All right. But the techniques that are more sophisticated than simply collecting data, that is from around this time frame. Okay. Now, as far as an overview of the chapter is concerned, let me show you this slide. Our book this begins in chapter 12, of course. Any statistics, basic statistics course, or course that broaches the subject of basic statistics, would have basically these sections. What we're doing today is basically discussing the basic techniques of gathering and organizing data. So this would be in our numbering system, section 12.1. Okay, and this is essentially the subject for today. All right, where we're headed for the rest of the week, and thereafter, the next thing would be actually presenting the data. That is, putting it on to some kind of a graph to organize it and disseminate. This is section 12.2. Types of averages is section 12.3. Types of position within data is also mentioned in section 12.3 from our book. 12.4 is types of variation. Right? 12.5 is frequency distributions of different type, but especially normal distribution. And then there's modeling, which in our case would just be limited to linear modeling. Right? This is known as regression. All right, section 12.6. All right. So think of it this way: today is Monday, Tuesday, Wednesday, Thursday. We're off. Pardon me. No, this is Monday, Tuesday, Wednesday. These two, and this is Thursday. All right. This is Monday next week, and Tuesday next week. So not too much left. All right. Anyhow, as I mentioned, this is a nice outline. Any book that you had, whatever, regardless of their numbering system, would have these subjects, right? And pretty much in this order. All right. You might have noticed when I mentioned in that other slide that probability was part of this, and probability was the tail end of MAT-114. Right? If you remember, if you took me, or if you had MAT-113, you know that what was it, chapter 11 was about probability. They have a lot of similarities, probability and statistics, but the purposes, the usages are different. All right. Anyhow, you'll notice that they're closely related. They share much of the same vocabulary, just maybe in a slightly different context. All right. So you have some familiarity. Do not be dissuaded. Okay. All right. Now, if you look at this handout, all right. What is statistics? Statistics is essentially the art and the science, the marriage of these two things, which is a beautiful thing. Art and science merged, all right, in a mathematical way. All right. Statistics is the art and science of collecting, organizing, presenting, and analyzing data, right? Which could be something as simple as counting people, or counting animals, or what have you, counting items to keep record, but really for the purpose of making predictions about the future, all right? If I could sell it, all right, I would always start with that. Tell your kids, you know, this is about predicting the future, right, in a mathematical way, and it's true, all right? Now, there's different branches, if you will, of statistics. There is what is referred to as descriptive statistics and inferential statistics. Descriptive statistics is the actual collected, organized, presented, analyzed numerical information. All right. Inferential statistics is, to use them again, it's the predicting portion of this, the making predictions and generalizations. All right. Hypothesis testing. All right. Remember, hypothesis from the from scientific method. Right. A hypothesis is a temporary answer to a question raised by some observation, right? And you design an experiment in the context of science, all right, to test your hypothesis. In mathematics, purely, all right, you test your hypothesis in statistics as well, all right? All right. If you could write an equation, that's basically you can think of the equation more or less as the experiment, right? And it will prove or disprove your hypothesis, your expectations or your suspicions, all right, about the data. Okay, you might think of it this way. All right, the descriptive statistics is the actual data. Whereas inferential statistics is a bit more akin to the actual purpose of the data. Right. Okay. For our purposes, this much of the actual equation writing, all right, this will be when we get to section 12.6, regression. Specifically linear regression, which is modeling something based upon y equals mx plus b, essentially. Okay. Now, let's see. What about the data itself? There's a slide for that. Okay. Where does the data actually come from? Well, again, there's a dichotomy here. The data ideally comes from measurements, right? It's an oversimplification to simply say that it's the numbers, you know. It depends on what the numbers actually are, you know. Ideally, if we're talking about anything scientifically based, it would be measurements, right? And these are referred to as the qualitative aspects. Okay, there's an alternative way of saying that. All right, what are regarded as quantitative aspects are the observations about something. It's more descriptive in that respect. All right, ergo is an example of each. What is an example of measured data? The measured heights of people in a group. You could take that data, all right, the different heights of people, which are probably close, you know, humans are humans, all right, and calculate an average, say, for example. All right. A qualitative aspect based upon observation might be the various colors of a lobster, all right, in a group, or many lobsters, right? You know that primarily in nature, at least, lobsters have sort of a red-green color to them. They look like the ocean, more or less, all right? But occasionally, you come across a blue lobster, you know. All right? That is an important characteristic, right? That distinction. All right. Now there's this concept. There's population and then there's sample. This will be especially important later. Think of population as basically being the whole group, and think of a sample as being basically part. is generally not the whole thing, right? To illustrate that, I drew this ellipse here. If the population is the entirety, I'll just illustrate that here. Right, again, i.e. the whole. Then a sample would be some chunk of the whole. So this might be a sample, as it's part of it. This might be a different sample, a part of it. This is a sample, and this is a sample. Now, in the context of statistics, a population is definitely the whole thing. All right, the whole group. All right, whatever you're working with. All right. The sample is ideally supposed to be representative of the whole without being the whole. So it's always going to be one less. All right. Now, as far as terminology is concerned, let me show you where this is similar to things you've already discussed in last semester and earlier this semester, or this course. So here's a table, as I like to use, for definitions. Good. And then we'll get to an example, which is interesting, I think. All right. Let's try to formalize this. Population. This doesn't look like it's writing too much better than the other marker. Is that too faint? I think it's basically visible. All right. Back to this one. Just as a little side note here, there's no symbol that I'm really going to be using here. In the context of set notation, remember sets, fancy braces? This might be the universal set. The universal set is all the parts in the box, you know, whether you use them or not. Or perhaps what you'll hear, you've heard in chapter 11, the total sample space. Key phrase there is total. Okay. That's more or less in the context of probability. For our purposes, the population is all items or people of interest. Right. The whole, right? The whole group. All right. In contrast to that, a sample. This cooperates. My markers are not so helpful today. Let me try this one. The sample is again a part of the group. A part of the whole. Alright. In statistics, not the whole thing. You know. At least one less. is ideally representative of the whole. Which means that even though it is a smaller chunk, right, it's a mixed bag just like the whole would be a mixed bag. I hope that that's visible, right? A sample is a part of the whole, in statistics at least, not the whole. It would be at least one less. One item, one person, one content. Right? It's ideally representative of the whole. Right? That key for operative term there is ideally. Right? In the context of probability, I'll put here again. This would be like the probability of an event. So if you remember the formula for probability, it's usually written like this. The probability of an event, whatever it is equal to the number of events favorable, number of outcomes favorable to that event over the total number in this sample space. Right. If again, you think of, in the context of probability, the population would be the whole kit and caboodle, the sample space, right, to really reinforce this concept, the total, right? Well, the number of outcomes favorable to the event would be some subset in the context of set notation. I didn't even spell correctly. Right. A subset or the probability of just an event. Okay. Now, lastly, before we move on to the example, I don't want to use green, it's not going to show up. Let's see. I'm going to go back to blue here, hopefully this works. You'll hear this phrase, unbiased sample. This is, again, a genuine representation or replica, you might say, of the population. That will be important later. An example to illustrate. And to that end, let me dig up the problem I have from another textbook. So if you look in word problems here, it'll be the very first page. I really like this. You probably will not have to do this too much in our class, but it's certainly something you can handle. And I think it's interesting because I've often wondered, how is it that biologists or zoologists or rangers, park rangers, are able to accurately estimate how many members of a species are wandering around? Well, this will help you figure that out. Yellowstone Park in Wyoming has the largest population of free-roaming bison in the world. Right, to approximate the total, a sample of 200 bison are captured, tagged, and released, which to me doesn't sound too pleasant for the bison, but this is how they count them. So they'll put something maybe in their ear or in an obvious place where they could see from a distance perhaps. A tag. Later, a total of 120 bison is observed by park rangers, 6 of which have the tags. Now let's assume for a second that the tags didn't fall off somehow naturally in the course of a bison roaming. All right. Write a proportion equation to approximate the total population of the free roaming bison. So a couple of things to note here. All right. The original sample, I'll put this in red, is 200 bison. All right. And they are tagged. All right. Later on, 120 bison are observed, and 6 of them are tagged. All right. So you have basically 3 figures to work with, all right, which would make, in theory, this should be proportionate. All right, it'd make it possible to write a proportion equation to approximate the total population without going up to every bison, which would be rather difficult, and counting them all individually. All right. So remember, if you write a proportion equation, it's essentially a ratio set equal to a ratio, a glorified fraction set equal to a glorified fraction. So 4 parts. All right. Hopefully that's visible. There's probably more than one way to arrange these 3 numbers, all right, but be consistent whatever way you decide to do that, all right, and do decide it before you start filling in the voids here. Let's think of it this way. There's, we'll call this the top and the bottom here to start with. In the context of this problem, the top will be a sample, otherwise known as a part, and I hope that that's visible. It doesn't look like it is. Is that a little bit easy to see? I think maybe. Okay. The top will be a sample or some part of the whole, and the bottom will be the population, ideally, or the total. The whole kit and caboodle. So as long as you're consistent, all right, divvy up the top here and the top here in the same way. All right. So the question is designed to approximate the total population of free roaming bison. So we don't actually know that. So what we could do is, in this case of this first ratio, let's just put X, all right, to represent that. The total free roaming bison. All right. Down here, rather. I'm sorry. I'm not taking my own advice when I should. Okay. In the second fraction, well, I'll finish this one. We already have the void filled in. The amount that we do know out of the total, out of X, is 200, right? $200 out of the total, so I will put a 200 here appropriately. In the second ratio, this is now the total, 120. All right, and the number of that, 6 out of 120. The 6 would go up here, because again, that's part of the whole. And that is the proportion equation. Now, how do you solve proportion equations? Remember, cross multiply. So you multiply this way, and write the abbreviation. 6 times x would be 6x, right? And then put an equals. And then you multiply, cross multiply this way. And it's 200 times 120. You could do the multiplication, of course, right? My instinct is never to multiply. It's sort of, I don't think that's visible enough. My instinct is to resist the temptation to multiply immediately. You might do that in the long run, but if you end up having to bring this 6 over here, and there is possibly some relationship between either of the factors. In the factored form, it might be a little bit easier to simplify. Whereas if you multiply these things together, it would be correct, but you get something much larger, and maybe it's not so obvious that there is a relationship. It depends on the figures. Anyhow, just for the moment, hold off on doing the actual multiplication. Just kind of leave a dot there to represent that they should be multiplied. All right. Now, if you're going to bring the 6 over to here, you do so, of course, by opposite operations. What is the opposite of multiplying by 6? It's to divide by 6, and you would do it to both sides. So I'm going to put a line underneath both of these things. All right. That leaves you with x, which is what you're actually looking for. And now, if you're not using a calculator, you could strategically take advantage of the factored form of this. Factors have dots or parentheses as separating the parts. So, there is definitely a relationship between 6 and 12. Right? They have a common factor of 6. Right. So, 6 divided by itself to simplify would be 1. Now you don't have a denominator anymore, really. 12 divided by 6 would be 2, with a 0 attached to it. Right? And then you have leftover 200 times leftover 20 to worry about. Right? 2 times 2 is 4. And you count the zeros, there's 3. So what you should end up with is 4,000 bison total population. This is essentially an indirect way of counting. It would be rather difficult, right? Especially if you're working in Yellowstone Park, which is probably enormous, you know. And going around and going up to a buffalo and going 1, and then finding a separate 1, 2, 3, and then counting 4,000 of them, you know. So, it may change from one day to the next. You never know what terrible thing will befall the poor animal. But this is a very good way to estimate mathematically using proportion equations, all right? This is why they tag animals. My point of using this, again, is to illustrate that there's a population, more or less a total of some sort, and a sample, which is just a portion of the whole. All right. Now, let's get into sampling methods. All right. It's fine to have this concept, but how does one actually get a sample? Why is it hot today? Well, let me back this a little bit to see the whole thing. All right. Take a look at this page. I'll make little notes. Okay. For our purposes, there are essentially 5 sampling methods. All right. Random sampling, cluster sampling, systematic, convenience, and stratified. This last one here, well, the one that's tucked in the middle, convenience sampling, is probably not the best one. All right, but these other ones have different conditions here. All right, not the best. Right? If something is a convenience, it's more or less an act of desperation. Think of it that way. Let's zoom in on this now, and we'll discuss these. That's the other ways of what. Okay. All right. Of these up here, well, you know what? The 2 on the side here. Random sampling is something that occurs when every individual, right? Emphasize this: every individual item or person or object, right, has an equal chance of being randomly selected. All right, every time that you do it. All right, a fairly close example of this would be something like drawing lottery balls. All right, if you have 100 of them, all right, on the very first draw, all right, unless somebody's cheating or something like that, any one of the balls has an equal chance of being selected. All right, and that's still true even after you do it again, and do it again, and do it again. All right. They all have an equal chance, right? Emphasize that, of being selected. Cluster sampling, I put this here because it is similar sounding, right? It's not when you're talking about individuals so much as you're talking about whole groups, right? So you can identify cluster sampling by that phrase, right? Every group, every whole group has an equal chance of being randomly selected. Right. Another cue that you're dealing with something like this is when they'll mention geographical location, right? Often pertaining to geographical areas that have been subdivided already, you know. So think of this as being a group of people, right? Every whole group has an equal chance, and think of this as being individuals have an equal chance. Okay? Very similar, right? Sorry, that's my radiator. Another there's a little cloud in between here on purpose. I wish I could show you the whole thing very large, but can't. All right. Let me do this first and I'll come back to the cloud. Systematic sampling is when you deliberately select every nth person or item. It's not quite random, right? You are purposely doing, let's just say, every 10th person. Okay, so if you see that, that's a cue. Again, a little hint that this is what's going on here. All right, when you see th, all right, suffix. All right, somewhere. It doesn't have to be 10th per se. It could be 9th or 20th or 100th or what have you. All right, but if it's deliberately picking every 10th or every nth of some sort, that's systematic. All right. Okay, an example of this would be something like decimation. Don't quote me on this, but Romans invented this means of punishment for their soldiers known as decimation. It's a little bit more complicated than just simply killing every 10th person, all right, but that's basically for whatever the soldiers did or didn't do, all right, but it's it's similar enough, all right. I think it might involve also a gang of 10 dudes, gang up on a 9th dude or whatever. 10 on 1 or 9 on 1. Anyhow, to take or do or affect every nth something, and decimation, some derivative of that is similar enough. All right, that is systematic. All right, now let me get back to this cloud here for a minute. A preliminary step were you to design a survey that would affect both random or systematic. In either one of these contexts, in either one of these situations, right, as a preliminary step, which is why I put an arrow pointing here and an arrow pointing down here. You might assign a number to each item and then decide a sample size, all right? In other words, choosing a random starting point to count also, right? All right, so in a lottery system, right, the balls are all numbered, right? If you're running an experiment of some sort, or rather a survey, right, you might assign a number to each of the people in the group, right? Then decide how many people you're going to take for your experiment, right? And if you're just doing it truly randomly, then you will randomly choose a number, right, rather than an individual by name or by site, right? If you're engaging in systematic sampling, you might strategically go, well, I want to use every 5th person, out of a group of 100, right? And you'll end up with what, 20 people in theory, right? So just think of that. There are two preliminary steps here: assigning a number to each, and then deciding a sample size, and choosing a random starting point. Now, you don't have to start from 0, right? You can just kind of go, randomly that person is the first person, and count from there. Okay? All right. Let's zero in on stratified here. It's very hot today. All right. I tried to organize this in some logical way. And it's unfortunate that I can't show you the whole thing clearly from a distance. Let me back this off for just a moment. That's as close as I'm going to get it, right? This side is about individuals. Right? Every individual, or every 9th individual, every 10th, nth, or what have you. And this side is about groups. Right? A whole group is randomly selected. And now we're getting into stratified, which also pertains to groups. All right. So let me zero in on that. All right, the stratified sampling here. This is when there's some organization that occurs to begin with. Stratified sampling is deliberately organizing into groups first, right? According to some similarity, all right? And then selecting several randomly from each group. All right, that's not quite the same thing, again, as the thing either adjacent or above it. All right? Cluster sampling is you take an entire group, all right? And each one, every group has an equal chance of being randomly selected, all right? This is a little bit more strategic than that, all right? You want individuals, all right? But you want to deliberately organize them according to some similarity first. There's a lot of sync there. And then you will select perhaps several from each of those groups, right? The best example I could think of is basically think about high school classmen, right? In a high school, there are freshmen, right? There are sophomores, there are juniors, and there are seniors. So if you were running some experiment on these students, do tell them ahead of time, of course. You need to ask their permission, that would be inappropriate otherwise. How are these groups already organized? Basically, they're organized according to age. Right? People who are 12 and 15 are freshmen, usually, right? Sophomores are 15 and 16. You know, juniors are 16 and 17. Seniors are 17 and 18 years old. Right? So you basically categorize people according to ages first. That's their similarity. Right? And that's enough of a similarity, right? Because the freshmen, especially in a public high school, right, is a mixed bag of people. Right? So that's an accurate representation of a whole too. Right? The whole would be the entire high school. Alright. This last thing here, convenience sampling, again, is more or less an act of desperation. Using what is available, alright, and it's quick. But it isn't necessarily reliable, which you have to be careful of. Get this out of the way, please. Alright. Convenience sampling is exactly what it sounds like. It's limited, but it's quick and easy. Alright, to say it with the emphasis on it's limited. It's quick and easy, but it's limited. Alright? It's a convenience. Alright, an example would be surveying the first 10 people who exit a building. Alright? Now, if your survey is about people who say, hate taxes, what you're trying to get a public opinion on taxes, don't go down to the IRS and start surveying the people who leave the building, right? Because they might be skewed one way versus another, Beware potential biases. People that frequent the same location might naturally share a narrower perspective on issues. I remember surveys are usually asking people's opinions about something. All right, so you have to be careful. All right, because the people exiting the IRS might just be the people who have been, they're not too happy having paid taxes. Now, who loves paying taxes, of course, right? But it is a necessary thing within reason. All right. You have to be careful, all right? So beware potential biases. All right? It might be easy to get information, but you don't necessarily want it. It's not going to be reliable, is the bottom line. Okay. Let's see. All right, let's do some other examples here. From word problems. And we could identify these. I left the solutions there so that you could test yourself if necessary. All right, let's see. All right, well, so I'll try to emphasize with a specific color here. I hope that's visible. I'm fighting the sun again. All right. Identify the sampling technique. Again, we have 5. Right? I'll put them up here. Random, cluster, systematic, stratified, and convenience sampling. All right. Those are your multiple choices. All right. Which do these most resemble? All right. Explain your answer. Every 20th soup can coming off an assembly line is checked for defects. All right. Based upon these 5 choices and certain cues, suspect phrases, what would you guess is the sampling method here? All right. If someone is strategically taking every 20th, all right, that would be systematic. Okay. B, a $50 gift certificate is given away at the annual bankers convention. Tickets are placed in a bin, and the tickets are mixed up. Let's see. Then the winning ticket is selected by a blindfolded person. Right. A couple of things here. They're placed in a bin. Right. The tickets are mixed up, and then they're selected by a blindfolded person. Right. So without saying the word, this would describe random selection. Right. If the gift certificate is given away, a $50 gift certificate is given away, and tickets are placed in a bin, and then selected by a person who is looking, all right, that's random selection. Okay. Let's see. C. Children in a large city are classified based on based upon the neighborhood school they attend. All right, a random sample of 5 schools is selected. All right, all of the children from each school are included in the sample. All right, now we're talking about a geographical area. We're talking about a city. All right, and the way that it's chopped up is neighborhood school. All right. Now it does say the word random here, which is useful to us, but we're not talking about individuals. We're talking about entire schools. All right. All children from each school selected are included. So this is an example of a cluster sampling. Right? Remember, cluster is also cued by area. They sometimes refer to it as area sampling instead. All right, but it's a cluster. All right. D. The first 50 people entering a zoo are asked if they support an increase in taxes to support zoo expansion. All right. Now, a couple of key phrases here. The first 50 people entering a zoo. All right. So not exactly random. All right. There may be a bias here because the people who frequent the zoo evidently like the zoo. All right, so you're not really getting an accurate representation of the entire population. All right, so do beware of that. There may be some bias. All right, you're asking them if they want to support an increase in taxes to support the zoo expansion. All right, again, they might be in favor of increasing taxes because they like the zoo. All right, but if you went down to, I don't know, the Pizza Hut and asked people about the zoo, you might get a more accurate representation of the total population, believe it or not, than Pizza Hut. No, not my favorite pizzeria, by the way. Not. This is an example of convenience sampling. All right, why? Because it's the first 50 people. All right, and it's really not being too conscientious about where you're asking them. You're asking people about the zoo at the zoo. All right, so that's not the best course of action. It's just an act of desperation. All right, convenience sampling. All right, last one here. All registered vehicles in the state of California are classified according to type. Here's a key phrase here: classified according to type. All right, subcompact, compact, mid-size, full-size SUV, and truck. A random sample, this is also helpful, a random sample of vehicles from each category is selected, right? Instead of high school classmen, freshmen, sophomores, juniors, seniors, all right, you're talking about vehicles, of course, but they're already classified according to some distinction. They're all vehicles to begin with, right? But you've organized them according to their sizes. All right, compact, subcompact, mid-size, full-size SUV, and truck. All right, so this is an example of stratified sampling. Okay. So for each of these, you should have systematic, random, cluster, convenience, and stratified. An example of each. All right, and we can verify now. Let's see. Yes. Systematic, random, cluster, convenience, and stratified. All right. To verify. Okay. Now the last thing here I'll leave you with for today is just a bit of advice, right? Especially as people who frequent the internet like we do, you get, especially during election year, a lot of statistics sort of blown you away, which are not necessarily reliable information, and you do have to be skeptical. Right? The best advice I could ever give anyone, all right, is to be skeptical of everything. Do the research yourself from reliable sources, multiple sources, all right, before you take anything at face value. All right? Here's a joke, all right, which I'm sure I've modified from its original author. Right, 99% of all statistics are made up, all right, including that one, including this. Okay, don't just believe things that people randomly say. All right, if you Google search this, I'm sure that 99% is easily replaced by some other percentage. Right, sounds important, right? Because it has numbers in it, right? So it sounds like it's math and therefore reliable, but it detect misuse, all right? Be suspicious, all right? Questions always to ask of quoted statistics or other information. And I don't have to put percentages or anything in it. All right, firstly here, all right, was the sample of sufficient size? Generally speaking, more data is more reliable, right? Now, you could have a bunch of, bumbled sort of experiments, right? And a lot of data taken into consideration, which is why I say general. But, it's slightly more trustworthy, all right, when you have more data, right? That means that in an ideal situation, an experiment has been tested a hypothesis has been tested many times, and hopefully proven every time, from multiple resources, right? Not just the same resources. Don't get the same people to run the same experiment. Something ideally, especially in science, should be repeatable everywhere, no matter who's doing them, within reason. All right, more data is more reliable. All right, second thing to consider, all right, was the data taken from an unbiased resource? All right. Again, there are, I'm sorry to say, nefarious people with an agenda out there in the world, especially on the internet, who they just want to substantiate their argument, but they do so illegitimately. All right, so they're, and you have to also be careful. Sometimes people, it's not even, consciously, all right, but they have a bias and it works its way into their results, okay? An unbiased sample is an accurate representation of the whole, right? So again, don't go down to the zoo and start asking people about the zoo, all right? Because, whether they like the zoo or not. That's just silly, right? Don't go down to the IRS and ask people if they like paying taxes. I'm sure you'll get some grumbles, all right? All right. Number 3 here. Is a statement ambiguous? All right, meaning does it have more than one meaning? Meaning. I hate green. It never writes. How about this one? That's a little bit better. Not much. Is a statement ambiguous? Sometimes, again, it isn't always intentional, but it might be subconscious even. But there are people who will, present information to you in a very subtle way that is, counting on you not knowing what the context is. All right. Truly factual information strives to be clearly defined. All right, not ambiguous, easily understood. All right, over-explained intentionally, like now. All right, it is purposely not vague. So if you come across a word that has, 2 different contexts, 2 different meanings, all right, 2 different intentions, all right, just be careful. Maybe somebody's trying to sell you something. Okay, so sample size needs to be large. Ideally, the larger the better. Generally, all right, from an unbiased resource and is clearly defined. All right. Okay. All right, that's enough of that. We are done for today, so I'll just let you loose here. Let me turn this off, remind you what your homework is, and that's it. Alright, if you're following along, remember for homework, if you want to do section 12.1 in my lab, okay? Do try to catch up if you haven't been on the ball too much, because just to show you the calendar really quick, we're nearing the end here. All right, we have this week and basically half of next week before we finish, okay? And everything is going to be due by this evening, okay? So make sure that you do that, all right? And then you're good to go. All right, thank you guys for sticking with me. I will see you again tomorrow. Be careful out there.